Most people look up at the night sky and see points of light scattered across darkness, peaceful and unchanging. But each of those distant stars may harbor worlds so extreme, so utterly different from anything we know, that they challenge everything we understand about planets. For centuries, scientists believed they could predict what planets should look like, how they should behave, where they should form. Time and again, the universe has proven them wrong, revealing environments so harsh and bizarre they seem almost impossible. Yet there they are, real and measurable, forcing us to expand our definition of what a world can be. In this video, we'll explore these extraordinary planets that exist at the very limits of what physics allows, from worlds where it rains molten glass to planets that drift alone through the darkness between stars. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Out there in the depths of space, scattered across distances that stretch far beyond anything we can truly imagine, there are worlds that would seem impossible if we hadn't actually found them. These planets orbit other stars, sometimes so close that their surfaces glow like molten metal, sometimes so far that they drift in eternal darkness. The universe, it seems, has no interest in following the quiet, predictable rules we might expect. For most of human history, planets were just those few bright dots wandering across our night sky. Mercury, Venus, Mars, the gas giants further out. We wondered if other stars might have their own families of worlds, but we had no way to know for certain. The problem was simple, really. Stars are incredibly bright, and planets are dim by comparison. It's like trying to spot a candle flame next to a massive searchlight from thousands of miles away. The light just overwhelms everything else. So astronomers had to get creative. They learned to watch for the tiniest wobbles in a star's position, caused by the gravitational tug of an orbiting planet. They measured incredibly small dips in starlight when a planet passed in front of its star, blocking just a fraction of the light. These changes were so subtle that detecting them required instruments of breathtaking precision, but it worked. In the 1990s, the first confirmed planet around a sun-like star was discovered, and everything changed. What surprised scientists wasn't just that these worlds existed, but how utterly strange many of them turned out to be. Some of the first discoveries were massive gas giants, larger than Jupiter, but orbiting so close to their stars that they completed an entire year in just a few Earth days. According to the theories of the time, this shouldn't have been possible. Planets like that should have been torn apart or boiled away. Yet there they were, defying expectations. This was just the beginning of a pattern that would repeat over and over. The universe, it became clear, doesn't care much about our theories. Planets can form in ways we didn't predict, migrate to orbits that seem impossible, and survive in conditions that would destroy anything we're familiar with. Some worlds have been found with atmospheres being stripped away by their stars' radiation, streaming behind them like invisible comet tails. Others have been discovered floating alone in the darkness between stars, rogue planets that were somehow ejected from their original solar systems. There's something deeply humbling about this realization. Our Earth, with its comfortable temperatures and gentle seasons, isn't the standard template for planets. It's just one variation in an enormous catalogue of possibilities. We tend to think of our world as normal, but normal is a concept that doesn't really apply when you're talking about planets. Normal is just what we happen to be used to. Consider the question of temperature. On Earth, we think of a hot day as perhaps 40 degrees Celsius. We consider anything below freezing to be quite cold. But there are planets out there where the average temperature is over 2,000 degrees, hot enough to melt most metals. The air itself, if you could call it air, would glow red hot. On the other extreme, there are worlds so cold that any atmosphere they once had has frozen solid and fallen to the surface like snow. Then there's the matter of gravity. Here on Earth, we're so accustomed to our planet's gravitational pull that we rarely think about it, but there are planets where the gravity is so strong that a person weighing 70 kilograms on Earth would weigh several hundred kilograms there. The very act of standing up would be exhausting. Your bones might not be strong enough to support your own weight. On other worlds, gravity is so weak that you could jump dozens of meters into the air with barely any effort. Weather on these distant worlds defies imagination too. There are planets where the wind speeds reach thousands of kilometers per hour, making the strongest hurricanes on Earth look like gentle breezes. Some worlds have storms that have been raging for centuries, massive cyclones that could swallow our entire planet. Others have rain, but not the kind we know. Instead of water, liquid methane falls from methane clouds. On some planets, it might rain molten glass, driven sideways by supersonic winds. The very concept of a day and night cycle becomes strange when you venture beyond our solar system. Some planets are tidally locked to their stars, meaning one side is in permanent daylight, while the other is trapped in eternal night. The day side might be hot enough to vaporize rock, while the night side is cold enough to freeze gases solid. Between these extremes lies a narrow twilight zone, where temperatures might be more moderate, a thin ring around the planet, where conditions could theoretically support some form of liquid water. Other worlds spin so quickly that a day lasts only a few hours. Still others rotate so slowly that a single day stretches on for weeks or months. Imagine watching the sun crawl across the sky so slowly that it barely seems to move at all. Or picture a world where the sun rises and sets multiple times in what we would consider a normal Earth day. The chemistry of these distant atmospheres is equally fascinating and alien. Earth's atmosphere is roughly 78% nitrogen and 21% oxygen, with traces of other gases, but planetary atmospheres can be made of almost anything. Some are thick with carbon dioxide, creating greenhouse effects so intense that the surface temperature is hot enough to melt lead. Others are rich in hydrogen and helium, like miniature versions of gas giant planets. A few have been found with atmospheres containing water vapor, which is exciting because water is essential for life as we know it. But perhaps the most intriguing are the atmospheres that contain more exotic substances. Clouds of silicate particles, essentially tiny grains of glass floating in the air, atmospheres with metallic compounds that might create shimmering, colorful skies unlike anything we've ever seen. Some worlds might have atmospheric chemistry so complex that the sky changes color throughout the day, or displays phenomena that would be completely alien to our experience. The discovery of each new planet adds another piece to an increasingly complex puzzle. Every world teaches us something new about how planets form, how they evolve, and what conditions are possible in the universe. Some planets orbit binary stars, experiencing the rise and fall of two different suns. Others follow highly elliptical orbits, experiencing extreme seasonal variations as they swing close to their star and then far away. There are planets that are older than our entire solar system, worlds that formed when the universe was young and have been quietly orbiting their stars for billions of years longer than Earth has existed. There are also planets that are surprisingly young, still forming in disks of dust and gas around newly born stars. These infant worlds give us glimpses of what our own solar system might have looked like in its early days. Perhaps most remarkably, there are planets that exist in the so-called habitable zone around their stars, the region where temperatures are just right for liquid water to exist on the surface. These worlds capture our imagination because they represent the possibility, however remote, of finding life beyond Earth. But even among potentially habitable planets, the variety is enormous. Some might be covered entirely by oceans. Others could be mostly desert. A few might have thick atmospheres that create a greenhouse effect, while others have thin atmospheres that provide little protection from cosmic radiation. The search for these worlds continues with increasingly sophisticated instruments and techniques. New telescopes can detect smaller planets, analyze their atmospheres in greater detail, and even begin to map their surfaces in some cases. Each technological advance opens up new possibilities for discovery. We're moving beyond simply finding planets to actually studying their properties in detail, understanding their weather patterns, their geological activity, and their potential for supporting life. What strikes many scientists is how this flood of discoveries has changed our perspective on our own planet. Earth no longer seems like the obvious, inevitable result of planetary formation. Instead, it appears to be one outcome among many possible outcomes, shaped by a specific set of circumstances that might be relatively rare in the universe. Our comfortable temperatures, stable climate, and protective magnetic field are not guarantees. They're the result of a complex interplay of factors that could easily have been different. This realization brings with it a certain philosophical weight. If Earth-like conditions are uncommon, then perhaps life itself is rarer than we once thought. Or perhaps life is more adaptable than we imagine, capable of thriving in environments that seem hostile to us. The truth is, we simply don't know yet. But every new planet we discover adds to our understanding of what's possible and brings us a little closer to answering one of the most fundamental questions we can ask. Are we alone in the universe? The light from these distant worlds has been traveling through space for years, decades, sometimes centuries before reaching our telescopes. In a very real sense, every observation is a message from the past, carrying information about worlds that might have changed dramatically in the time it took their light to reach us. Some of the planets we're discovering today might no longer exist, destroyed by stellar explosions or swallowed by their expanding stars. Others might have evolved in ways we can't yet imagine. There's something both humbling and inspiring about this cosmic perspective. We're part of a universe that is far stranger, more diverse, and more creative than anyone imagined just a few decades ago. The planets we're discovering challenge our assumptions about what's normal, what's possible, and what conditions might support the emergence of life. They remind us that the universe is under no obligation to conform to our expectations or our theories. The universe keeps its secrets hidden in the faintest whispers of light, scattered across distances so vast that patience becomes the astronomer's most essential tool. For centuries, humans gazed up at the night sky and wondered whether other stars might harbor worlds like our own. This question lingered in the realm of speculation, because wonder, no matter how deep, cannot sustain scientific inquiry without something tangible to measure. The challenge of finding planets beyond our solar system reveals itself when you consider the physics involved. A planet produces no light of its own, merely reflecting a tiny fraction of what it receives from its host star. Even Jupiter, massive as it appears to us, would vanish into insignificance when viewed from the distance of another star system. The star's brilliance overwhelms any feeble reflection from its orbiting companions by factors of thousands, sometimes millions. This overwhelming brightness forced astronomers to abandon the obvious approach of looking directly for planets. Instead, they began asking more subtle questions about the invisible effects these worlds might have on their stars. Gravity, that fundamental force binding the cosmos together, provided the first breakthrough. When a planet orbits a star, both objects actually revolve around their common center of mass. The star, being far more massive, barely moves, but it does move, creating a tiny wobble as it responds to its planet's gravitational pull. This motion produces something measurable through an effect discovered in the 19th century. As the star wobbles toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. This Doppler effect, the same phenomenon that changes the pitch of an ambulance siren as it passes by, became astronomy's first reliable method for detecting unseen worlds. The precision required staggers the imagination. Astronomers measure stellar velocities changing by mere meters per second across distances spanning hundreds of trillions of kilometers. The first confirmed planet discovered around a sun-like star using this technique appeared in 1995, orbiting the star designated 51 Pegasi. This world defied every expectation astronomers had developed about planetary systems. Here was a gas giant, larger than Jupiter, racing around its star in just over 4 days. The temperatures on this world exceeded anything found in our solar system. Its very existence forced scientists to reconsider fundamental theories about how planets form and migrate through their stellar neighborhoods. That discovery opened floodgates of possibility. If one such world existed, countless others must be waiting for detection. Meanwhile, astronomers developed another approach that relied on cosmic geometry rather than stellar motion. Sometimes, purely by chance, a planet's orbit aligns perfectly with our lines of sight to its star. When this happens, the planet passes directly in front of the star from our perspective, blocking a small fraction of its light. These transits create measurable dips in stellar brightness, often less than 1%, sometimes far less. The regularity of these dips reveals the planet's orbital period, while their depth indicates the planet's size relative to its star. This transit method transformed exoplanet discovery when space-based telescopes eliminated the blurring effects of Earth's atmosphere. The Kepler Space Telescope, launched in 2009, embodied the patience that astronomy demands. For years, it stared unblinkingly at a single patch of sky, monitoring over 150,000 stars simultaneously. The quiet persistence of that mission speaks to something profound about scientific discovery. Kepler simply watched, night after night, recording tiny fluctuations in starlight, waiting for patterns to emerge from apparent randomness. When those patterns finally revealed themselves, they transformed our understanding of the galaxy's architecture. Thousands of planet candidates appeared in Kepler's data, revealing that planetary systems represent the rule rather than the exception among stars. Statistical analysis of Kepler's discoveries suggests that most stars host at least one planet, with many harboring entire families of worlds. This abundance challenges our sense of cosmic uniqueness, while simultaneously making the universe seem more familiar, populated by countless variations on the planetary theme we know from our own solar system. But knowing that a planet exists tells us little about what kind of world it might be. Temperature, atmospheric composition, weather patterns all remain hidden behind the overwhelming glare of the host star. Here, astronomers found yet another subtle approach. When a planet transits its star, some starlight passes through the planet's atmosphere before reaching our telescopes. Different atmospheric gases absorb specific wavelengths of light, leaving characteristic fingerprints in the stellar spectrum. Decoding these atmospheric signatures requires extraordinary precision, like determining the ingredients of distant soup by analyzing wisps of steam. Yet modern instruments make such measurements possible, revealing the presence of hydrogen, sodium, water vapor, methane, and other molecules in alien atmospheres. Each detection adds another piece to the puzzle of what these distant worlds might actually be like. Other discovery methods exploit even more exotic physics. Gravitational microlensing relies on Einstein's prediction that massive objects bend spacetime itself. When one star passes almost directly in front of another, more distant star, the foreground star's gravity acts like a lens, magnifying the background starlight. If the lensing star has planets, they create brief additional brightening events, tiny ripples in the light curve that betray their presence. This technique proves especially valuable for finding planets far from their stars, worlds that other methods might miss entirely. Some microlensing discoveries have revealed planets apparently drifting alone through interstellar space, no longer bound to any star, perhaps ejected from their birth systems during violent gravitational encounters. Direct imaging, the most obvious approach, remains the most challenging. Special instruments must block out a star's overwhelming glare to reveal the faint glow of orbiting planets. Success comes mainly with young, massive planets still radiating heat from their formation, making them visible in infrared light, despite their vast distances from Earth. The ingenuity required for these discoveries reflects humanity's remarkable ability to find signals hidden in noise, to detect the almost undetectable through clever combinations of physics and patience. Each method demands not just advanced technology, but entirely new ways of thinking about what to look for and how to interpret the universe's subtle communications. Discovery in this field rarely arrives as a sudden revelation. More often, evidence accumulates gradually, patterns emerge slowly, and understanding develops through careful analysis by teams of scientists working across years or decades. There exists something deeply reassuring about this process. The way careful observation and methodical analysis eventually reveal truths hidden in apparent randomness. The scales involved humble our everyday experience. Astronomers routinely measure stellar wobbles of mere meters per second across distances that light takes decades to cross. They detect brightness changes, smaller than the shadow cast by an insect crossing a distant street lamp. These measurements push at the very limits of what physics allows us to detect, yet they consistently reveal new worlds orbiting distant stars. This ongoing exploration reminds us that the universe often whispers its secrets rather than shouting them. The most profound discoveries frequently emerge not from dramatic events, but from patient accumulation of precise measurements, careful analysis of subtle patterns, and the gradual recognition that what seemed like random noise actually contained the signatures of entire worlds, waiting to be understood. As astronomers accumulated more and more discoveries of worlds beyond our solar system, a striking pattern began to emerge. The diversity of planetary types was staggering, far beyond what anyone had imagined when we first started looking. There were massive planets, bigger than Jupiter, racing around their stars in orbit tighter than Mercury's path around our Sun. Some worlds appeared to be made mostly of iron, creating densities that seemed almost impossible. Others were so bloated and light that they resembled giant bubbles of superheated gas, barely clinging together under their own weak gravitational pull. Each new find was like adding another unusual piece to a cosmic jigsaw puzzle. The neat, orderly picture of planetary systems that once filled astronomy textbooks was slowly being replaced by something far more chaotic and interesting. Our instruments kept getting better too. Telescopes on the ground and in space became incredibly sensitive. Computer programs for analyzing the data grew more clever and sophisticated. Space missions were designed specifically to study these distant worlds in ways we'd never attempted before. The James Webb Space Telescope can now peer into the atmospheres of planets dozens of light years away. It can identify individual molecules floating in alien skies, measure temperatures with remarkable precision, detect the chemical fingerprints of compounds that exist under conditions we've never experienced. Just a generation ago, this would have seemed like pure fantasy. We've reached a fascinating turning point in our understanding of the cosmos. The question is no longer whether other stars have planets orbiting them. Now we want to know what those planets are actually like. How did they form in the first place? How do they change over millions of years? How extreme can conditions become before a world simply can't exist anymore? Because when astronomers started looking closely at these distant worlds, they found places that weren't just different from Earth. They were radically, almost impossibly different. Worlds where physics and chemistry get pushed to their absolute limits. Places with temperatures that would vaporize solid rock, winds that move faster than sound waves, entire atmospheres being slowly torn away by the radiation from their parent stars. When scientists describe a planet as extreme, they're not being dramatic for the sake of it. In scientific terms, extreme means something very specific. It refers to conditions that fall way outside the range of what we consider normal or familiar. Places where temperature, pressure, gravity, or chemical processes reach levels that challenge our basic assumptions about how planets are supposed to behave. Once you start looking for these extreme conditions, you realize the universe has an almost artistic talent for creating them. It helps to think first about what we instinctively consider normal. For most of us, the word planet brings to mind the handful of worlds we know well. Earth, obviously, with its comfortable temperatures and breathable atmosphere. Mars, cold and dusty, but still recognizable as a place you might imagine walking around. Jupiter, enormous and stormy, but still operating according to physical laws that make intuitive sense. Even Venus, despite its crushing atmospheric pressure and surface hot enough to melt copper, still feels like part of our familiar cosmic neighborhood. But as the catalogue of exoplanets has grown, that sense of familiarity has started to fade. Our solar system, it turns out, might actually be pretty unusual, maybe even rare, Many planetary systems are arranged in ways that would seem completely chaotic if we tried to compare them to our own. Giant planets orbit where you'd expect to find small rocky worlds. Some planets follow tilted orbits, or get stretched into elongated paths that carry them on wild swings toward and away from their stars. There are worlds that complete an orbit in just a few hours, and others that take thousands of years to circle their star just once. So what exactly makes a planet extreme? There isn't really a single answer to that question. Instead, astronomers think about boundaries, limits that physics and chemistry can sustain. A planet becomes extreme when one or more of its characteristics approaches those fundamental limits. Heat is probably the most obvious way a world can become extreme. A planet's temperature depends mostly on how far it orbits from its star, but that's just the beginning of the story. The makeup of the atmosphere matters enormously. Whether the surface reflects light or absorbs it, how heat gets moved around by winds and ocean currents. All of these factors play important roles in determining what conditions are actually like on the surface. Even considering all that complexity, some planets orbit so close to their stars that the amount of energy they receive is almost unimaginable. Think about Mercury, the innermost planet in our solar system. At midday near the equator, temperatures can reach about 430 degrees Celsius. That's hot enough to melt lead into liquid metal, but by the standards of exoplanet research, Mercury isn't considered particularly extreme. There are worlds out there where temperatures climb above 2,000 degrees, even 3,000 degrees Celsius. That's hot enough to turn solid rock into vapor. On places like that, the normal distinction between solid and gas starts to break down completely. Minerals that form mountains and continents on Earth would float around as glowing clouds in the atmosphere. Winds might carry droplets of molten stone across the sky, condensing and falling like rain wherever temperatures drop just slightly. It's almost impossible to picture, because nothing in our everyday experience gives us a reference point for landscapes made of liquid rock or clouds composed of iron vapor. And yet, according to our best measurements and computer models, these conditions aren't just theoretically possible. They're real. They exist right now on worlds we can actually observe. Heat is just one way planets can push the boundaries of what seems possible. Gravity is another fascinating dimension of planetary extremes. The strength of gravity on any world depends on how massive it is and how large it is. A planet much more massive than Earth can create surface gravity 2, 3, or even 10 times stronger than what we experience here. If you could somehow stand on a world like that, every single movement would feel incredibly heavy. Lifting your arm would require serious effort. Walking would be slow and exhausting. Even breathing might feel strange, as your chest worked harder against the weight of your own body pressing down. Astronomers have found many planets called super-Earths, rocky worlds that are significantly larger than our own planet. On these worlds, gravity might be several times stronger than Earth's gravity. These places aren't necessarily hostile in every way, but their environments would be profoundly unfamiliar to anyone used to life here. Mountains probably couldn't rise as high because rock under very strong gravity tends to collapse under its own weight. Atmospheres would likely be much denser, pressed much closer to the surface. At the opposite extreme are planets with very low densities, sometimes called puffy planets. These worlds can be enormous in diameter, but surprisingly light in terms of total mass. They're composed mostly of hydrogen and helium that's been heated until it expands dramatically. Their gravity at the outer atmospheric layers might actually be quite gentle, even though their total mass is immense. Orbital mechanics provide another pathway to planetary extremes. In our solar system, most planets travel in nearly circular paths around the Sun, maintaining relatively stable distances throughout their year. But many exoplanets follow highly elliptical orbits, swinging very close to their stars, and then drifting far away again in endless cycles. During the closest approach, temperatures on these worlds may become scorching hot. At the farthest point in their orbit, the same planet cools down dramatically. These worlds experience seasonal changes, far more intense than anything we see on Earth, though calling them seasons hardly captures the incredible scale of environmental change involved. There are also planets that have become tidally locked to their stars, meaning one hemisphere always faces the star, while the other side remains in permanent darkness. On worlds like this, the contrast between day and night reaches extreme levels. The star-facing side might be hot enough to melt metal, while the night side could be cold enough for atmospheric gases to freeze solid and fall to the surface like snow. Between these two extremes lies a narrow twilight region, a thin band that circles the planet like a permanent ring of sunset and sunrise. Conditions in this twilight zone might be less severe than either extreme, creating a unique environment unlike anything in our solar system. Wind systems can reach extraordinary speeds under conditions like this. When the temperature difference between day and night sides becomes large enough, the atmosphere begins moving in powerful currents, trying to redistribute heat around the planet. Some exoplanets have measured wind speeds of several kilometers per second. That's faster than the speed of sound traveling through air. These aren't gentle breezes, but massive roaring rivers of gas that sweep across entire hemispheres. Atmospheric pressure represents another factor that can push planets into truly extreme territory. Deep inside gas giant planets, pressures can climb to millions of times the atmospheric pressure we experience at Earth's surface. Under such incredible conditions, even hydrogen, the lightest and simplest element, begins to behave in completely unfamiliar ways. It can become metallic, conducting electricity like copper wire. These exotic states of matter are incredibly difficult to create and study in laboratories here on Earth. Yet they might exist naturally inside the cores of many large planets throughout the galaxy. The universe routinely creates conditions that represent the cutting edge of our scientific understanding. Chemistry itself can take surprising forms under extreme planetary conditions. Atmospheres rich in carbon, sulfur, or other elements can produce cloud formations and weather patterns completely unlike anything we observe here. On some worlds, the combination of temperature and pressure allows chemical compounds to form that would be totally unstable on Earth's surface. The sky itself could display colors and patterns that would seem utterly alien to human eyes. Radiation adds yet another dimension to planetary extremes. A world orbiting very close to an active star gets bombarded by intense ultraviolet light, X-rays and other high-energy radiation. This energy can heat the upper layers of the planet's atmosphere until gas molecules begin moving fast enough to escape into space entirely. They form vast streams of material, flowing away from the planet like an enormous invisible tail. Over millions of years, processes like this can strip away much of a planet's original atmosphere, leaving behind a smaller, denser core that might be completely different from what the world started as. These are the kinds of conditions astronomers have in mind when they talk about extreme worlds. Heat intense enough to turn rock into gas, gravity strong enough to reshape entire landscapes, winds faster than the speed of sound, radiation powerful enough to gradually erode away entire atmospheres over geological time. But there's another sense in which these planets represent extremes, and it has less to do with specific numbers and more to do with expanding our concept of what's possible. Each new discovery forces scientists to refine and improve their understanding of how planets form and change over time. Every time we find a world that doesn't fit our existing models and theories, those models have to be adjusted or completely rebuilt. In this way, extreme planets function almost like natural experiments conducted by the universe itself. They show us what happens when starting conditions vary widely, when orbits shift and migrate over time, when stars behave differently than our sun, when chemistry unfolds under circumstances we've never encountered before. They expand the range of what we consider possible in this cosmos. It's worth remembering that extreme doesn't necessarily mean permanent or unchanging. Planetary systems evolve slowly over immense spans of time. Orbits can migrate inward or outward. Atmospheres can be lost to space or gained from comets and asteroids. Temperatures rise and fall as parent stars age and change their energy output. A planet that seems impossibly extreme today might not have been that way in the distant past. It might not remain extreme in the far future either. There's something oddly comforting about this perspective. The universe isn't a static, frozen place. It's an environment of gradual change, of slow processes unfolding over timescales that dwarf human history. Even the most hostile and extreme worlds we can imagine are temporary arrangements, brief chapters in much longer stories that span billions of years. Every exoplanet that astronomers find teaches us something new about how strange worlds can really be. Among all the unusual planets discovered so far, none are quite as fascinating as the ones we call lava worlds. These are places where the ground isn't solid like we know it, but instead exists as glowing, molten rock that flows and shifts under incredible heat. Picture a planet where the surface temperature climbs above 2000 degrees Celsius. At that point, rock doesn't just get hot, it melts completely. The familiar stones and minerals we walk on every day become thick, glowing liquids that behave more like honey than solid ground. It's a transformation that challenges how we think about what a planet's surface should be. Most of these lava worlds exist because they orbit incredibly close to their stars. Some circle their suns in less time than it takes us to get through a single day on Earth. Imagine having a year that's shorter than the time between breakfast and bedtime. The gravitational dance that keeps these planets so close also means they're constantly bathed in intense stellar radiation. KTOT B stands out as one of the first lava worlds studied in detail. This planet completes its entire orbit in less than 24 hours. The side facing its star reaches temperatures that would melt almost any material we can think of. Scientists believe vast oceans of molten rock stretch across that hemisphere, their surfaces churning slowly in a state that glows with its own heat. What makes these worlds even more remarkable is that many are tidally locked. Just like our moon always shows the same face to Earth, these planets keep one side permanently facing their star. This creates a dramatic split between eternal day and endless night. The day side experiences relentless heat, while the night side never sees starlight at all. This temperature difference creates something almost unimaginable. A rock cycle driven by evaporation and condensation of minerals themselves. On the scorching day side, rock doesn't just melt, it can actually evaporate into vapor. These mineral gases rise into the atmosphere, drift across to cooler regions, and then condense back into solid form. It's like the water cycle we know on Earth, except with stone behaving like clouds and rain. The physics behind this process reveals how even materials we consider permanent can change state under extreme conditions. When temperatures climb high enough, substances we think of as forever solid can become gases that float through an atmosphere. It challenges our everyday understanding of what different materials can do. Kepler-10b represents another example of these extreme environments. This rocky world orbits so close to its star that its surface likely resembles a global lava field. Its year lasts less than one Earth day, and its high density suggests a composition rich in heavy elements, possibly with a massive iron core at its center. Studying these distant worlds requires incredible ingenuity since we can't see detailed images of their surfaces. Instead, astronomers analyze how their brightness changes as they orbit, measuring thermal emissions and infrared radiation. By watching how much heat comes from the day side versus the night side, scientists can build models of what conditions might be like on these alien landscapes. 55 Cancri E draws attention as a lava world roughly twice Earth's size but much denser than most planets of similar radius. It completes its orbit in just 18 hours. Observations suggest its surface temperature varies significantly across different regions, perhaps because lava flows solidify in some areas while remaining molten in others. There was once speculation that this planet might be rich in carbon, possibly containing vast amounts of diamond in its interior. That idea has since been reconsidered as new data became available, which illustrates something important about planetary science. Our understanding constantly evolves as better measurements become possible. Early theories get refined, or sometimes replaced entirely, as the picture grows clearer. The concept of lava weather opens up fascinating possibilities. Just as Earth's weather comes from water evaporating and condensing, these worlds might experience similar processes with vaporized rock. Winds could carry silicate vapors across the planet, where they cool and fall as mineral droplets or particles. Standing on the boundary between hot and cool regions, if it were somehow possible, you might see skies hazy with mineral vapor and ground that glows faintly from its own internal heat. Rivers on such worlds wouldn't be water, but slow streams of molten stone, moving gradually under gravity. The landscape would be shaped by flows of liquid rock rather than the erosion patterns we see on Earth. It's a completely different way for a planet's surface to evolve and change over time. Tidal heating provides another mechanism for creating lava worlds, one that doesn't depend entirely on stellar proximity. Jupiter's moon Io demonstrates this process in our own solar system. Gravitational interactions between Jupiter and neighboring moons flex and compress Io repeatedly, generating heat that drives intense volcanic activity. Some exoplanets may experience even stronger tidal forces, especially if their orbits are slightly elliptical. As these planets move closer to and farther from their stars, gravitational stresses heat their interiors from within. This means some lava worlds are essentially heated by the cosmos itself, their surfaces constantly renewed by volcanic activity driven by orbital mechanics rather than just stellar radiation. This reveals how dynamic planets can truly be. It's tempting to imagine worlds as static objects, unchanging spheres drifting through space, but many of them are active, evolving, constantly reshaped by heat, impacts, and internal motion. They're participants in an ongoing cosmic dance, rather than passive observers. Atmospheric loss represents another fascinating aspect of lava planets. When rocky worlds orbit extremely close to their stars, intense radiation can strip away lighter atmospheric elements. What remains might be a thin envelope of heavier gases mixed with vaporized rock. Some planets develop extended tails of escaping material, like cosmic comets made of gas and dust, rather than ice. Over long periods, this process gradually erodes planets, reducing their mass and changing their character. It reminds us that worlds aren't necessarily permanent in the forms we observe today. They can lose material, migrate in their orbits, or even be torn apart under sufficiently extreme conditions. The timescales involved carry their own quiet fascination. A lava ocean on a distant planet might persist for millions or billions of years, far longer than any geological process on Earth has remained unchanged. From our perspective, such worlds seem eternal, yet in the broader history of planetary systems, they might represent just one phase in a much longer evolution. Modern telescopes are beginning to study lava planets in unprecedented detail. Instruments capable of analyzing light from these distant worlds reveal clues about their composition and temperature. Some observations hint at surface changes over time, suggesting lava flows shift and reshape landscapes in ways we're only beginning to understand. This level of detail, extracted from points of light many light-years away, demonstrates the remarkable precision of contemporary astronomy. It also deepens our appreciation for the incredible variety that planetary environments can achieve across the universe. Whether lava worlds might once have been more temperate raises intriguing questions about planetary migration. A world that gradually moves inward over time could have experienced cooler conditions earlier in its history. Its present molten state might represent only the final stage of a long transformation, with surfaces that slowly heated and melted as orbital positions changed. Such possibilities remind us that planetary systems evolve, sometimes dramatically, as gravitational interactions shift the positions of worlds over cosmic timescales. What we observe today may be just one snapshot in a much longer story of change and adaptation across the universe. When we think about the hottest places in the universe, our minds might drift to glowing volcanic planets or the surfaces of distant suns. But some of the most extraordinary temperatures ever recorded actually belong to worlds that have no solid ground at all. These are the ultra-hot Jupiters, massive spheres of gas that orbit so close to their stars, they challenge everything we thought we knew about what a planet could endure. Consider our own Jupiter for a moment. It's a cold, distant giant, drifting far from the sun where temperatures plummet to around -145 degrees Celsius. The sunlight there is weak, filtered through layers of thick atmosphere, creating a world of storms and swirling clouds in perpetual twilight. Now imagine taking that same massive planet, or one even larger, and slowly moving it closer and closer to its star, closer until its year becomes just a few days long, closer still until a complete orbit takes less than 24 hours. At such distances, the amount of energy hitting the planet becomes almost incomprehensible. The atmosphere doesn't just warm up, it begins to transform entirely. It expands, glows, and starts behaving in ways that stretch our understanding of weather itself. Take WASP-12b, for instance. This world whips around its star in just over one Earth day. Its temperature soars past 2500 degrees Celsius, hot enough to melt copper, hot enough to tear apart the very molecules that make up gases we're familiar with. The atmosphere of such a planet isn't the calm, layered structure we see on Jupiter. Instead, it becomes a turbulent, glowing envelope of superheated gas. The star's gravity is so intense that it actually stretches the planet out of shape, pulling it into an oval form like a cosmic egg. And perhaps most remarkably, the planet is slowly evaporating. Streams of gas are being stripped away from its outer layers, forming vast clouds that spiral around the star. Its destruction in slow motion, unfolding over millions of years, invisible to human timescales, but relentless nonetheless. The chemistry happening in these atmospheres is something from another world entirely. Literally. At such extreme temperatures, iron, the same metal that forms our tools and buildings, exists as vapor floating in the upper atmosphere. On planets like Kelt 9b, one of the hottest worlds ever discovered, temperatures reach over 4000 degrees Celsius. That's hotter than the surface of some small stars. At these temperatures, molecules simply can't hold together. Hydrogen, oxygen, metals, they all exist in a dissociated state, torn apart into individual atoms, creating an atmosphere that resembles the outer layers of a star more than anything we'd recognize as planetary. The winds on these worlds are equally extraordinary. Because many ultra-hot Jupiters are tidally locked, one side always faces the star while the other remains in permanent darkness. The temperature difference between these hemispheres creates atmosphere currents. Unlike anything in our solar system, computer models suggest winds that reach several kilometers per second, far exceeding the speed of sound in their own atmospheres. These aren't gentle breezes, they're perpetual hurricanes spanning entire hemispheres, carrying superheated gas from the day side toward the eternal night. As clouds form a tool on these planets, they're not made of water droplets or ice crystals. Instead, they might consist of silicates or metal oxides condensing at high altitudes, where temperatures drop just enough to allow it. In some regions, astronomers believe that molten iron droplets might condense and fall as rain, only to evaporate again as they descend into hotter layers below. It's weather, but weather that stretches the very meaning of the word. Many of these planets appear strangely inflated, like cosmic balloons. The intense heating from their stars causes their atmospheres to expand dramatically, making them larger than Jupiter despite having similar or even smaller masses. Some become so diffuse that if you could somehow place them in an ocean vast enough to hold them, they would actually float. Their density becomes so low that they challenge our basic assumptions about what planetary matter should look like. The very existence of these worlds raises fascinating questions about planetary formation. According to our best theories, gas giants should form in the cold outer regions of planetary systems, where ice and gas are abundant. For a Jupiter-sized planet to end up so close to its star, it likely formed much farther out and then migrated inward over time. This migration might happen through interactions with the disk of gas and dust from which the system formed, or through gravitational encounters with other planets. This process reveals something profound about planetary systems. They're not static arrangements frozen in time. They're dynamic, evolving structures where worlds can wander, sometimes slowly, sometimes dramatically, reshaping the architecture of their entire system as they go. Our own solar system, with its relatively stable and widely spaced planets, might be just one possible arrangement among countless others. Elsewhere, giant planets may have swept inward, scattering smaller worlds, or fundamentally altering the paths of everything around them. Studying these extreme worlds has taught us enormous amounts about atmospheric physics, under conditions we never imagined possible. By observing how they absorb and emit light, scientists can determine what elements are present and measure temperature structures throughout their atmospheres. When these planets pass behind their stars, in events called secondary eclipses, telescopes can isolate the planet's own light and analyze its composition. These measurements have revealed atmospheres containing water vapor, carbon monoxide, sodium, and other elements, sometimes in completely unexpected proportions. There's something almost philosophical about contemplating these worlds. They challenge our comfortable notions of what a planet should be. They're not places where life could exist, not stable or temperate environments. They're violent, dynamic, and often short-lived on cosmic timescales. Yet they're planets nonetheless, shaped by gravity, orbiting their stars, part of the vast diversity of worlds that populate our galaxy. Despite their harshness, there's something mesmerizing about imagining them. Picture a giant sphere of glowing gas, its shape stretched and distorted by tidal forces. Winds racing across its atmosphere at impossible speeds, clouds of vaporized metal forming and dissolving in endless cycles. All of this unfolding under the relentless blaze of a star so close, it fills half the sky. As our telescopes become more sensitive, astronomers are discovering smaller planets in similarly extreme orbits, some rocky, others intermediate in size between Earth and Neptune. Each new discovery expands our understanding of how close a world can orbit and still survive, how atmospheres behave under extreme radiation, and how planetary systems can evolve in ways we're only beginning to comprehend. These ultra-hot Jupiters remind us that the universe is filled with worlds beyond our wildest imagination, places where the familiar rules of weather and chemistry are pushed to their absolute limits, creating environments both terrible and beautiful in their extremity. Out beyond our solar system, there are worlds where the sun never moves. These planets hang in space, showing the same face to their star for eternity. One side bakes in endless daylight, while the other freezes in permanent darkness. It's a phenomenon called tidal locking, and it might be more common than the familiar dance of day and night we know on Earth. The process itself is surprisingly gentle. Gravitational forces act like invisible brakes, slowly reducing a planet's rotation over millions of years. Eventually, the planet settles into a rhythm where it spins once for every orbit around its star. We actually see this happening right above us. Our moon is tidally locked to Earth, which is why we always see the same craters in Maria looking down at us. But when an entire planet becomes locked this way, especially one orbiting close to its star, the consequences unfold on a massive scale. The day side absorbs energy continuously, with no relief from nightfall to cool things down. Temperatures can soar past 2,000 degrees Celsius. Meanwhile, the night side radiates its heat into the void of space, growing colder and colder as eons pass. You might imagine such a world would simply split into two extremes, a blazing desert facing one way, a frozen wasteland facing the other. Sometimes that's close to the truth, but atmospheres rarely behave so predictably. Air has a tendency to move, to flow, to seek balance. When one region heats intensely and another doesn't, pressure differences emerge. Gas flows from high-pressure areas to low-pressure areas, just like water flowing downhill. On our planet, these pressure differences give us trade winds and jet streams. On tidally locked worlds, the same physics operates, but amplified beyond anything we experience. Computer models suggest that winds form enormous streams, carrying heat from the day side toward the night side in great atmospheric rivers. Sometimes these currents are so powerful that the hottest spot on the planet isn't directly under the star, but gets pushed slightly to one side by the flowing air. There's something almost poetic about this. Even under the most extreme conditions imaginable, atmospheres still follow the same fundamental rules that govern weather everywhere in the universe. The scale changes, the intensity changes, but the underlying physics remains constant. Between the eternal day and eternal night lies a narrow band called the terminator zone. Here, the star sits permanently on the horizon, neither rising nor setting. Temperatures in this twilight region might be less extreme than on either hemisphere. Scientists speculate that on certain rocky planets, this zone could offer conditions where liquid water might exist, provided the atmosphere is thick enough to moderate the temperature. Imagine standing in such a place. The sky would hold a constant twilight glow. Walk in one direction, and you'd head toward a blazing, bright desert. Walk in the other direction, and you'd enter an endless frozen darkness. The wind might blow steadily from the hot side to the cold side, carrying clouds along a continuous path that never changes. The thickness of a planet's atmosphere plays a crucial role in determining how livable such a world might be. A thin atmosphere can't transport heat effectively, so the temperature contrast between day and night becomes severe. The night side could grow so cold that gases begin to freeze out of the air entirely, forming frost deposits of atmospheric components. Over long periods, this process could gradually strip away the night side's atmosphere, locking those gases into ice. A thick atmosphere tells a different story. It can transport heat more efficiently, smoothing out temperature differences and preventing out temperature differences. This is why astronomers pay such close attention to atmospheric composition when studying distant worlds. Small differences in atmospheric pressure can lead to dramatically different climates. These tidally locked planets are especially common around red dwarf stars. These stars are smaller and cooler than our Sun, so their habitable zones, the regions where liquid water could theoretically exist, lie much closer to the star. Planets orbiting in these zones are very likely to become tidally locked over time. The TRAPPIST. One system offers a perfect example. This red dwarf hosts several Earth-sized planets, many of which scientists believe are tidally locked. Researchers are studying them carefully, trying to determine whether their atmospheres might be thick enough to transport heat and maintain stable climates. There's something almost unsettling about imagining life on such a world. On Earth, our daily rhythms are deeply connected to the cycle of day and night. We wake, we work, we rest, all guided partly by the rising and setting sun. On a tidally locked planet, that cycle wouldn't exist. Time would still pass, but the sky wouldn't mark it. The star would remain fixed in the same position, and shadows would never move. It's difficult to picture how that might feel, to live where the lighting never changes, where morning and evening become meaningless concepts. Yet, from a purely physical perspective, these conditions are entirely natural outcomes of gravitational forces acting over vast spans of time. Studying these distant worlds requires incredibly sensitive instruments. Astronomers often measure infrared radiation to understand how heat is distributed across a planet's surface. As the planet orbits its star, different regions come into view, and the amount of heat being emitted changes slightly. These subtle variations allow scientists to infer temperature patterns and atmospheric circulation. Cloud formation on tidally locked planets follows its own strange logic. On the day side, intense heating may cause strong upward convection, leading to thick cloud layers that reflect incoming starlight back to space. On the night side, cooler temperatures allow different types of clouds to form, perhaps composed of materials that would seem exotic by Earth standards. In some computer models, large, bright cloud formations gather near the substellar point, the region directly facing the star. These clouds act almost like a natural parasol, providing shade for the surface below. The distribution of these clouds influences both the planet's temperature and its appearance from space. Even worlds of eternal day aren't truly static. Heat rises, winds flow, clouds form and dissipate. The atmosphere remains in constant motion, creating a dynamic system despite the unchanging position of the sun. The geology of rocky tidally locked planets tells its own story. The day-side heat could drive intense volcanic activity, especially if the planet's interior retains energy from its formation. Lava flows might reshape the surface repeatedly, while the night side preserves older terrain in the deep cold. Over millions of years, such differences could produce hemispheres with completely different landscapes, one constantly renewed by volcanic activity, the other largely unchanged since ancient times. As our instruments become more sophisticated, astronomers continue refining their understanding of how atmospheres behave under these extreme conditions. Each new observation adds detail to a picture that's still being assembled, piece by piece. What emerges from these studies is a recognition that planets exist along a spectrum of conditions. They're not simply hot or cold, habitable or inhospitable. Distance from the star, atmospheric composition, rotation rate, and internal heat all play interconnected roles. Small differences in any of these factors can lead to dramatically different outcomes. Perhaps most remarkably, tidally locked planets aren't rare exceptions in the galaxy. They may actually be among the most common types of worlds, particularly around red dwarf stars, which are themselves the most numerous stars in the universe. This means that worlds of permanent day and night may far outnumber planets like Earth, with its familiar rhythm of sunrise and sunset. That realization quietly shifts our perspective. The daily cycle that feels so fundamental to life, as we know it, may not be the default pattern for planets at all. In the vast catalogue of worlds that likely exist throughout the galaxy, Earth's rotating days and nights might be the unusual case, while the eternal twilight zones of tidally locked worlds represent the more typical planetary experience. The winds that tear across distant worlds make Earth's hurricanes look like gentle summer breezes. Out there in the depths of space, there are planets where the air moves faster than sound itself, creating permanent storms that never end, never rest, never give the surface a moment of peace. Picture a world where one side always faces its star, baked in relentless heat, while the other half stays locked in eternal cold. The temperature difference between these two sides isn't just a few degrees, like the difference between day and night here on Earth. We're talking about differences of hundreds, sometimes thousands of degrees. That kind of contrast does something dramatic to the air above. When you heat air, it expands, it rises, it wants to move toward cooler places. On these tidally locked planets, this creates circulation patterns that span the entire globe. The hot air from the day side rushes toward the night side in massive rivers of wind, reaching speeds that would make a jet engine seem slow. Scientists have measured wind speeds on some of these distant worlds that hit several kilometers per second. To put that in perspective, the fastest winds ever recorded on Earth barely reach a few hundred meters per second during the most violent tornadoes. These alien winds are in a completely different league, moving at velocities that create a continuous, roaring jet stream wrapping around the entire planet. HD 18-97333 sits about 64 light-years away from us, and it's become something of a celebrity in the world of extreme weather. This planet doesn't just have fast winds, it has winds that carry something truly remarkable through its atmosphere. The upper layers of this world contain clouds made of silicate particles, tiny grains that are basically the same materials we find in sand and glass here on Earth. But here's where it gets really interesting. At the temperatures found in this planet's atmosphere, these silicate materials can condense into microscopic grains that get suspended in the air. When supersonic winds grab hold of these particles, they don't fall down like normal rain. Instead, they get whipped sideways across the planet in sheets of flying glass. Think about that for a moment. Rain that doesn't fall, but flies horizontally at thousands of miles per hour. It's not the gentle patter of water droplets we know, but a constant, abrasive storm of glass particles that never stops, never settles, just keeps racing around the planet in an endless cycle. This kind of weather exists because the same forces that drive it never change. The star keeps heating the day side, the night side stays cold, and the winds keep flowing. There's no seasonal variation, no calm periods, no eye of the storm where things get peaceful. It's a permanent state of atmospheric chaos. These supersonic winds, do more than just move particles around, though. They're also moving heat, redistributing energy from the hot side to the cold side of the planet. Sometimes this creates an interesting effect where the hottest spot on the planet isn't directly under the star, but gets pushed eastward by the flowing atmosphere. Astronomers can actually detect this by measuring the infrared light coming from different parts of the planet as it orbits its star. They can create temperature maps that show how heat moves through the atmosphere, revealing the invisible rivers of wind that carry warmth around these distant worlds. WASP 76b offers us another glimpse into just how extreme these conditions can get. On the day side of this planet, temperatures climb so high that iron, solid iron, turns into vapor and floats around in the atmosphere like water vapor does in Earth's clouds. The winds then carry this iron vapor toward the cooler night side, where it condenses and potentially falls as droplets of molten metal. Iron rain. It sounds like something from a fantasy novel, but it's just physics playing out under extreme conditions. The same processes that give us water rain on Earth, evaporation and condensation, happen with entirely different materials when temperatures soar high enough to melt and vaporize metals. What's fascinating is that these alien weather systems follow the same basic rules as Earth's atmosphere. Pressure gradients still drive wind formation, hot air still rises, cool air still sinks. The difference is just in scale and composition. Instead of water clouds, you might have clouds of vaporized rock or metal. Instead of gentle trade winds, you get permanent supersonic jet streams. The intense radiation from these planets' nearby stars adds another layer of complexity. High-energy ultraviolet light breaks apart molecules in the upper atmosphere, creating layers of ionized gas that can interact with magnetic fields to produce aurora displays far more powerful than anything we see near Earth's poles. At these extreme wind speeds, the atmosphere itself becomes turbulent in ways that are hard to imagine. Shock waves form as the gas moves faster than sound. Different layers of the atmosphere mix and churn in complex patterns that even our most advanced computer models struggle to simulate accurately. The challenge for scientists studying these worlds is that we can't see any of this directly. We can't watch the storms unfold or track the movement of glass rain across alien skies. Instead, we have to piece together the story from incredibly faint signals, tiny variations in starlight that hint at the dramatic processes happening light years away. It's like trying to understand what's happening in a distant city by watching how its lights flicker through thick fog. You have to be incredibly careful about interpreting the signals, but gradually, patterns emerge that tell you something real is happening over there. The progress in this field has been remarkable, though. New instruments that can analyze infrared wavelengths have opened up entirely new ways of studying atmospheric dynamics on distant planets. Each year brings new techniques for extracting more information from those faint signals crossing the vast emptiness of space. These supersonic winds can actually reshape the way clouds form and move across a planet's surface. Instead of the relatively stable cloud patterns we see on Earth, these worlds might have clouds stretched into bands and arcs by high-speed currents, creating atmospheric patterns that shift and evolve on timescales much faster than anything we're used to. In some cases, the winds are so powerful that they're gradually stripping away the planet's atmosphere altogether. The supersonic flows carry material up to the outer edges of the atmosphere, where stellar radiation and solar wind can carry it away into space. Over millions or billions of years, this process could completely transform a planet's mass and composition. There's something profound about contemplating these worlds. Here on Earth, we check the weather forecast. We notice if it's getting cloudy, we might complain about a particularly windy day. But out there in the universe, weather can take forms that stretch our imagination to its limits, driven by energies and forces that dwarf anything in our everyday experience. What's equally remarkable is how these discoveries were made. No one directly observed glass rain or iron precipitation on these distant worlds. Instead, scientists started with tiny clues, subtle shifts in spectral lines, careful measurements of how heat is distributed across a planet's surface. From these fragments of evidence, they built up detailed pictures of entire atmospheric systems in motion. there's a quiet elegance to that process. You begin with almost nothing, just faint variations in starlight, and through careful analysis and the application of physical principles, you end up with knowledge of winds racing around worlds you'll never visit, storms that have been raging for millions of years, rain made of materials that would seem impossible under earthly conditions. These violent, seemingly inhospitable worlds are actually part of the natural diversity of planetary systems throughout the galaxy. They remind us that the universe isn't constrained by the gentle, stable conditions we're used to. It's capable of creating environments that push matter and energy to their absolute limits, sculpting worlds in ways that challenge our understanding of what's possible. In contemplating these extreme atmospheres, we gain not just scientific knowledge, but a deeper appreciation for the incredible variety of ways that physical laws can play out across the cosmos. Every planet is an experiment in physics, a unique combination of mass, energy, and chemistry that produces its own version of what it means to have weather, to have an atmosphere, to be a world spinning through space. Imagine a world that exists almost like a shadow against the brilliance of its star. These planets challenge everything we normally expect about how worlds should look. Most planets we know about shine back at us, reflecting the light that hits them. Earth bounces back roughly 30% of the sunlight that reaches our atmosphere. Venus acts like a cosmic mirror, with its thick clouds reflecting so much light that it becomes one of the brightest objects we can see in our night sky. Even our own moon, grey and dusty as it appears, still reflects about 12% of the light that touches its surface. This reflection is what astronomers call albedo, and it's how we typically see planets in the first place. When you look at Jupiter through a telescope, you're seeing sunlight that has traveled millions of miles, struck the planet's cloud layers, and bounced back toward your eyes. But scattered throughout the universe are planets that work completely differently. These worlds absorb nearly everything that falls upon them. They're darker than coal, darker than the blackest asphalt, darker even than materials specifically designed on Earth to trap light. One famous example, a gas giant called Tree S2b, reflects less than 1% of the starlight that reaches it. If you could somehow observe this planet up close, it wouldn't look like Jupiter with its familiar bands and swirling storms. Instead, you'd see something resembling a faintly glowing ember, illuminated only by the dim red heat radiating from its own atmosphere. The planet would appear as an almost perfect silhouette, swallowing light rather than scattering it back into space. The chemistry behind this darkness reveals something fascinating about planetary atmospheres. Many bright worlds owe their reflectivity to clouds, layers of tiny particles that scatter light in all directions. On Earth, water droplets create white, puffy clouds. On Venus, sulfuric acid particles form the brilliant reflective layer we observe from space. But on extremely hot planets, temperatures become too high for these reflective clouds to form properly. Instead, the atmosphere fills with gases that excel at absorbing light. Compounds like sodium, potassium, and titanium oxide capture incoming radiation and convert it directly into heat. The starlight penetrates deeper and deeper into the atmosphere, getting absorbed layer by layer, with almost nothing escaping back into space. High temperatures also break apart molecules that would normally condense into cloud particles. Without these clouds to scatter light, the atmosphere becomes clearer, but paradoxically much darker. It's like removing a lampshade. The light can travel further inward, but there's nothing left to redirect it back outward. Some of these dark worlds develop high-altitude hazes, made of complex hydrocarbons and other particles. These hazes become incredibly efficient at absorbing light, creating planets with deep, muted appearances. Saturn's moon Titan shows us a smaller-scale version of this process, where thick orange haze filters and dims the sunlight reaching the surface. On distant exoplanets with stronger radiation and different atmospheric chemistry, similar hazes can become even more effective light absorbers. They transform entire worlds into nearly perfect absorbers, cosmic objects that seem to drink in the light of their stars. What makes these dark planets especially intriguing is that despite appearing nearly invisible in regular light, they can still be studied and understood. Infrared observations reveal the heat they emit, allowing astronomers to measure their temperatures and analyze their atmospheric composition. In some cases, the contrast between their visible darkness and strong infrared emission actually makes them easier to detect in thermal wavelengths than in reflected light. This creates planets with a peculiar dual nature. They're dark and nearly invisible in the light we're used to, yet they glow brightly in heat signatures. They reveal themselves through warmth rather than brightness, like cosmic furnaces that absorb everything and radiate it back as thermal energy. The darkness of these worlds isn't just about appearance, it actively shapes their behavior and climate. A planet that absorbs most of the light it receives will heat much more efficiently than one that reflects a large portion of that energy back into space. This enhanced heating can dramatically raise atmospheric temperatures and alter circulation patterns, potentially creating more intense winds and accelerating chemical reactions throughout the atmosphere. There's something quietly profound about imagining a dark planet orbiting a brilliant star. From a distance, the star would shine with tremendous brightness, yet the planet itself would remain almost invisible, detectable only as a faint silhouette crossing the stellar disk during a transit. The planet would be massive, real, and physically significant, yet visually subdued, revealing itself only through careful scientific measurement. This reminds us that brightness doesn't always correlate with importance or significance. Some of the most interesting objects in the universe aren't the ones that shine most brilliantly, but rather the ones that quietly absorb, transform, and radiate energy in less obvious ways. As astronomical techniques continue to improve, scientists are discovering more planets with unusually low albedos. Each discovery provides another opportunity to study atmospheric chemistry under extreme conditions. By comparing these dark worlds with brighter planets, researchers can better understand how temperature, atmospheric composition, and stellar radiation interact to shape planetary climates over time. Rocky planets might also exhibit very low reflectivity under the right conditions. A surface composed primarily of dark basaltic rock would absorb much of the incoming starlight. If such a world lacked reflective clouds or ice deposits, its overall appearance could be remarkably dim, even if it were otherwise similar in size and mass to Earth. Imagining what it might be like to stand on such a world creates an unusual mental picture. The sky might appear much darker than we'd expect, with the host star blazing overhead, yet the landscape around you absorbing most of that light. The ground would have a muted, shadowed quality, with colors appearing subdued and contrast softened by the general lack of reflection. Even such a world wouldn't be completely without its own form of beauty. The intense glow of the star above, the faint shimmer of heated air rising from warm surfaces, perhaps the distant sight of another planet or moon hanging in the darkened sky. All of these would still create a landscape governed by the same physical laws that shape every corner of the universe. These dark planets also demonstrate that extreme planetary conditions don't always manifest as violent storms or chaotic environments. Sometimes extremity takes the quieter form of relentless absorption, of light steadily disappearing rather than scattering, of heat building gradually in atmospheres that capture and hold onto nearly every photon they receive. It represents yet another example of the incredible variety of planetary environments that exist throughout the cosmos, and the many different evolutionary paths that nature can follow when sculpting worlds under different physical conditions. Water shapes entire worlds in ways we're only beginning to understand. Some planets exist where liquid water doesn't just fill oceans, but covers everything. No continents poke through the surface, no islands break the endless expanse, just water stretching from horizon to horizon, hundreds of kilometers deep. These aren't the familiar seas we know. Earth's oceans seem shallow by comparison. On a true water world, you could drill down for hundreds of kilometers through liquid water before hitting anything solid. The ocean floor, if you can call it that, might not even be rock. Under such crushing pressure, water itself freezes into exotic forms of ice, denser than the liquid above it. This high-pressure ice behaves completely differently from the ice cubes in your freezer. Instead of floating, it sinks. Scientists have created these strange ice forms in laboratories, where water molecules get squeezed into crystal structures that don't exist anywhere on Earth's surface. On Jupiter's moon Europa, layers of this exotic ice probably sit beneath the liquid ocean, separating it from the rocky core below. Planet formation explains how these water worlds come to be. Young planetary systems start as swirling disks of dust and gas around newborn stars. Close to the star, temperatures run too hot for water to stick around, so rocky planets form instead. But farther out, in the cold depths of space, ice accumulates easily. Some of these icy worlds migrate inward over millions of years, drifting closer to their star's warmth. When they reach the right distance, all that ice melts into a global ocean. Since these planets began with far more frozen water than Earth ever had, their oceans grow extraordinarily deep. The pressure down there becomes almost unimaginable. Earth's deepest ocean trench reaches about 11 kilometers down. On a water world, you might descend 10 times that depth and still be swimming through liquid water. The weight pressing down would crush any submarine we could build. Kepler 22b gives us a real example to consider. This planet sits in the habitable zone around its star, where temperatures allow liquid water to exist. Its size and density suggest it could be exactly this type of water world, though we can't know for certain from this distance. Another candidate, GJ1 214b, presents an even more intriguing puzzle. Light passing through its atmosphere reveals thick clouds or hazes that hide whatever lies beneath. Computer models suggest vast oceans might exist under that shrouded atmosphere, but the planet keeps its secrets well hidden. Imagine standing on the surface of such a world. The horizon stretches endlessly in every direction, an unbroken line where water meets sky. No beaches exist, no cliffs rise from the waves, no familiar landmarks break the monotony, just water everywhere you look. Weather patterns would develop on scales we can barely comprehend. Storm systems could grow massive, drawing energy from the warm ocean surface below, then travel completely around the planet without hitting land. Waves might circle entire hemispheres, building into enormous swells that roll on for thousands of kilometers. Cloud formation would likely dominate the sky. With so much water surface area evaporating constantly, thick cloud layers would reflect sunlight back to space, creating a bright, diffuse illumination during the day. The entire atmosphere might become saturated with water vapor, creating a powerful greenhouse effect that traps heat and keeps temperatures stable across the globe. At night, if the planet had a moon, its reflection would stretch across the ocean in an unbroken path of light. No shoreline would interrupt that silvery trail. No headlands would cast shadows into the water. The view would be simultaneously beautiful and alien. The question of life on these worlds fascinates scientists. Water serves as a key ingredient for life as we understand it, so vast oceans seem promising, but water worlds might lack other essential elements. On Earth, life benefits from nutrients that wash off continents into the sea, and from chemical exchanges between seawater and the rocky seafloor. Without continents, and with exotic ice layers potentially isolating the ocean from the planet's interior, life on water worlds might need to find different pathways. Perhaps biological processes could develop around chemical gradients within the ocean itself, or around underwater volcanic activity if it exists. Temperature layers would probably form in these deep oceans, similar to Earth's seas, but on a much grander scale. Sunlight would warm the upper layers while the depths remained cold and dark. Currents might circulate slowly through the vast depths, driven by differences in temperature and density, distributing whatever nutrients exist through the water column. The scale challenges human imagination. Even Earth's oceans seem immense to us, containing water that would take centuries to explore thoroughly. A water world's ocean might contain 1,000 times more water, with depths that dwarf our deepest trenches. The pressure at the bottom would create an environment of crushing weight and perpetual darkness. Scientists study these distant worlds using clever techniques. By measuring a planet's mass and radius, they calculate its average density. If that density falls between rock and gas, it suggests significant amounts of water or ice. Spectroscopy can detect water vapor in planetary atmospheres, though determining whether that water exists as vapor, liquid, or ice requires careful analysis. Recent space telescope observations have begun detecting water signatures in exoplanet atmospheres. Each measurement adds another piece to our understanding of these distant oceans, gradually building a picture of worlds that exist in the space between rocky planets and gas giants. Tidal forces might shape these oceans in dramatic ways. If a water world orbits close to its star, or if it has a large moon, tides could rise and fall with tremendous power. Without continents to channel and focus these tidal surges, they might sweep across the globe as slow, powerful waves that lift the entire ocean surface. Weather systems would interact with the ocean on a planetary scale. Strong winds could drive enormous waves across thousands of kilometers of open water. Lightning might illuminate vast expanses of sea during storms that dwarf Earth's hurricanes. The atmosphere and ocean would exist in constant motion, exchanging energy and momentum. These worlds occupy a special place in our growing catalogue of planetary types. They're not gas giants with their thick atmospheres and no solid surface. They're not rocky desert planets with no atmosphere at all. Instead, they represent something in between, worlds where liquid water dominates the surface environment. Studying water worlds also changes how we think about our own planet. Earth's particular combination of land and sea, with its moderate oceans and diverse environments, might not represent the most common type of world in the universe. Perhaps most planets are either entirely covered by water, entirely covered by rock, or entirely frozen. Each new discovery expands our sense of what planets can become, reminding us that the universe contains far stranger and more wonderful places than we once imagined. Water worlds represent just one example of how nature explores different possibilities, creating environments that challenge our assumptions about what constitutes a habitable world. When we think about planets, we imagine them circling their stars in neat, predictable patterns. But the universe doesn't always follow our expectations. There are worlds out there, countless worlds, that have no star to call home. They wander through the galaxy completely alone, carrying nothing but the leftover warmth from when they first formed. These are rogue planets, and they might be some of the loneliest objects in the entire cosmos. The idea sounds almost like science fiction, doesn't it? A planet just drifting through empty space with no sun to light its way. For the longest time, scientists assumed this was impossible. Planets were supposed to stay put, orbiting their stars for billions of years in nice, orderly systems. But gravity, it turns out, can be a troublemaker. When planetary systems are young and still forming, things can get quite chaotic. Picture newly born planets, massive and gravitationally hungry, pulling and pushing on each other. Sometimes these interactions get violent. Two planets might have a close encounter, and one gets flung inward toward the star, while the other gets shot outward at incredible speed. If that outward momentum is strong enough, the planet escapes its star's gravity completely. It becomes a wanderer, starting a journey through the galaxy that could last forever. Scientists call this gravitational ejection, and computer simulations show it happens more often than we ever imagined. Some estimates suggest there could be as many rogue planets as there are stars in our galaxy. That's potentially hundreds of billions of these dark, solitary worlds. Finding them is incredibly difficult, though. Without a star nearby to light them up, rogue planets are nearly invisible. They emit only the faintest infrared glow, the last traces of heat from their birth. Young rogue planets are easier to spot because they're still relatively warm, but older ones fade to almost nothing. Astronomers have gotten creative with detection methods. There's something called gravitational microlensing. Where a rogue planet passes in front of a distant star, the planet's gravity acts like a lens, bending and brightening the star's light for a few hours or days. It's like catching a shadow that casts light instead of darkness. Recent discoveries have been particularly fascinating. Scientists have found groups of planetary mass objects floating freely in star-forming regions. Some are only a few times heavier than Jupiter, yet they're completely unbound to any star. They seem to have formed like regular planets, but were either kicked out early or never got captured by a stellar system at all. Imagine, for a moment, what it would be like to stand on such a world. The sky would be permanently black, filled with stars that shine clearer and brighter than anything we see from Earth. There would be no atmosphere scattering light from a nearby sun, so the view of space would be absolutely pristine. No sunrise would ever break the horizon, no sunset would ever paint the sky. The ground beneath your feet could be almost anything. Some rogue planets are probably gas giants, massive balls of hydrogen and helium, with no solid surface. Others might be rocky worlds, frozen solid, with any oceans they once had locked away under thick sheets of ice. But here's where it gets interesting. Some could have thick atmospheres that trap heat, keeping subsurface oceans liquid despite having no sunlight at all. This possibility has scientists quite excited. We tend to think of sunlight as essential for life, but deep in Earth's oceans, near hydrothermal vents, entire ecosystems thrive on nothing but chemical energy from our planet's interior. If a rogue planet had enough internal heat and good insulation from ice or atmosphere, it could maintain liquid water for millions or billions of years. Any life in such a place would exist in permanent darkness, guided by chemistry rather than photosynthesis. It would be a completely alien kind of biosphere, one that challenges our assumptions about where life can take hold. The thought reminds us that life, much like planets themselves, might find ways to persist in the most unexpected places. The temperatures on these worlds tell their own story. Without stellar radiation, the surfaces would be brutally cold, often just a few dozen degrees above absolute zero. Atmospheres, if they exist, might freeze out completely and fall as exotic snow, nitrogen and methane coating the ground in crystalline layers. But deep inside these planets, things could be quite different. Radioactive decay in their cores produces heat, and in large planets, this warmth can stay trapped for billions of years. Gas giants especially can maintain relatively comfortable interior temperatures long after they've been ejected from their birth systems. Some rogue planets might not be entirely alone in their journey. When a planet gets ejected, it could carry its moons along for the ride, held by gravity, even as it drifts through interstellar space. Picture a small moon orbiting a faintly glowing planet in the darkness between stars. The only light would come from the planet itself, perhaps reflected off icy moon surfaces. There would be no seasons, no changing sky, just the steady dance of celestial mechanics playing out in cosmic isolation. Over the vast timescales of galactic history, even these wandering worlds might not stay isolated forever. A rogue planet could pass near another star system, getting briefly warmed by alien sunlight before continuing its journey. In rare cases, it might even get captured by a new star's gravity, finding a second home after eons of wandering. The existence of rogue planets changes how we think about space itself. The regions between stars aren't empty voids. They're potentially filled with countless unseen worlds, each carrying its own history through the galactic night. Every one of these planets has a story, a unique composition, a particular path through the cosmos that brought it to its current state. Detecting more of these worlds requires incredible patience and sophisticated technology. Infrared telescopes and sensitive detectors are gradually revealing them, each discovery adding to our understanding of how planets are distributed throughout the galaxy. It's becoming clear that worlds aren't just confined to the neighborhoods around stars. They're scattered everywhere, in ways we're only beginning to comprehend. From our perspective, rogue planets might seem impossibly lonely, but they're products of the same cosmic processes that created every other world we know. They formed in disks of gas and dust, were shaped by gravity, heated by collisions and radioactive elements. Their paths diverged dramatically, but their origins connect them to planets like our own Earth. There's something profound in that connection. Even a world drifting alone in the space between stars is still part of our galaxy, still following the same physical laws, still carrying within it the history of cosmic evolution. In a strange way, these wandering planets remind us that the universe is far more dynamic and surprising than our everyday experience might suggest. The galaxy is filled with stories we're only just beginning to read, written in the motion of worlds we can barely see. When we peek beyond our own little cosmic neighborhood, something becomes clear. We've been looking at the universe through a pretty narrow lens. For the longest time, scientists thought planets came in just a few basic flavors. You had your small rocky ones, like Earth and Mars. Then the big gassy ones, like Jupiter and Saturn. And finally, those in-between ice giants, Uranus and Neptune. It all seemed so neat, so organized, like the universe had a preference for keeping things simple. But then we started finding planets around other stars, and everything changed. Suddenly, we were discovering worlds that didn't fit into any of our carefully organized categories. There were planets bigger than Earth, but smaller than Neptune. Some were made of combinations of rock, water, and gas, in mixtures we'd never seen before. Others were so massive, they sat right on the edge between being a planet and being what we call a brown dwarf. Those strange objects too big to be planets, but too small to become stars. These discoveries forced us to realize something humbling. Our solar system, familiar as it feels, might actually be pretty unusual. The most common types of planets in our galaxy are ones we don't even have here. Think about that for a moment. We've been studying planets for centuries, but the planets we know best might be the exceptions, not the rule. Scientists started calling these new worlds super-Earths and megaplanets. Despite the name, a super-Earth isn't necessarily anything like our Earth. The term just means it's bigger than our planet, but smaller than Uranus or Neptune. Some of these worlds are rocky, some are covered in water, others are wrapped in thick, dense atmospheres. The name describes size, not whether you'd want to live there. Imagine standing on one of these super-Earths. If that were even possible, your weight might double or even triple. Compared to what you feel here on Earth, mountains couldn't grow very tall, they'd collapse under their own weight before reaching great heights. If there's an atmosphere, it would be compressed into a thick, heavy layer close to the surface. The air might be so dense, it would create permanent clouds and haze that never clears. One of the first super-Earths to really capture scientists' attention was discovered back in 2007. At first, researchers thought it might be habitable, but later studies showed it was probably way too hot for life. Still, finding it proved that rocky planets larger than Earth weren't just possible, they were actually pretty common out there. Then came an even more surprising discovery, a planet with 17 times Earth's mass, but still rocky rather than gaseous. Before finding this world, most scientists believed that any planet that massive would inevitably collect thick layers of hydrogen and helium gas, becoming a gas giant. This discovery shattered that assumption, showing that under the right conditions, you could have truly massive rocky planets. The physics inside such a world would be unlike anything we know. The pressure deep in its core would be immense, far beyond what exists inside Earth. Minerals would be crushed into dense forms we've never seen before. The boundary between the planet's mantle and core might behave in completely unfamiliar ways. Even the gravity at the surface would create weather patterns that are hard to imagine. Winds might move strangely through the dense air, clouds could form much closer to the ground, rain would fall faster and harder, carving landscapes in ways we can barely picture. There's another category of strange worlds, called mini-Neptunes. These planets sit between Earth and Neptune in size, but they're made mostly of gas, or what scientists call volatile substances. They might have incredibly deep atmospheres, sitting on top of layers of water or exotic forms of ice. There might not be any solid surface at all, at least not in any way we'd recognize. One well-known example of this type seems to be made largely of water, or other light materials compressed by pressure into exotic states we don't see on Earth. When scientists try to study its atmosphere, they see thick clouds or haze that make it impossible to see deeper. But its overall properties tell us it's completely unlike any planet in our solar system. Here's what makes all this even more fascinating. These super-Earths and mini-Neptunes appear to be among the most common types of planets in the entire galaxy. Survey after survey suggests that many stars host planets in this size range, yet our own solar system has none of them. That absence is itself a mystery. Why did our system end up with small rocky planets and large gas giants, but nothing in between? Scientists are still trying to figure that out. Moving to even larger scales, we find planets that stretch the very definition of what a planet can be. Some are so massive they're almost brown dwarfs, those failed stars we mentioned earlier. The dividing line between a really big planet and a brown dwarf is usually placed at around 13 times Jupiter's mass. That's roughly the point where nuclear fusion can start happening in the interior. But the boundary isn't perfectly clear, and sometimes classifying these objects depends as much on how they formed as on how massive they are. There are planets still forming today, enormous worlds accumulating material from disks of gas and dust around young stars. Watching such a planet grow offers a rare glimpse into how planetary systems evolve. Some of these forming worlds may be several times more massive than Jupiter, and they're still getting bigger. Scientists have found planets with more than 10 times Jupiter's mass, orbiting at distances where they stay relatively cool. These massive worlds have incredibly strong gravity, and atmospheres so deep their interiors might contain layers of metallic hydrogen, under pressures far greater than anything in Jupiter's core. The existence of such massive planets raises profound questions about the limits of planetary formation. How large can a planet become before it crosses the threshold and becomes a star? Nuclear fusion requires extreme temperatures and pressures, and only objects above a certain mass can sustain it. Below that threshold, even the largest planets remain dark, radiating only leftover heat from their formation billions of years ago. These massive worlds don't just exist in isolation, they actively shape their entire planetary systems. A really massive planet can alter the orbits of smaller worlds, or even eject them completely from the system. In some cases, giant planets appear to have migrated inward, disrupting the formation of smaller planets closer to their star. This process might explain why some stars have hot Jupiter-type planets, but no small rocky worlds nearby. The giant planet moving inward through the disk of material may have scattered or absorbed much of the matter that would otherwise have formed Earth-like worlds. Super-Earths also challenge everything we think we know about planetary geology. On a planet with 2 or 3 times Earth's gravity, tectonic plates might behave completely differently. Volcanoes, mountain formation, even the way heat flows from the interior to the surface could follow patterns we've never seen before. The thickness of the crust, the movement of the mantle, all of it might be governed by physics we can only guess at. Then there's the question of atmospheres. A planet with stronger gravity can hold on to lighter gases much more easily. It might retain thick layers of hydrogen or helium that would escape from a smaller world. This could create hybrid planets, partly rocky and partly gaseous, with deep atmospheres sitting on top of solid interiors. From a distance, such a world might look like a gas giant, but beneath its clouds, there could be a dense rocky surface under crushing pressure. Studying these distant worlds requires combining multiple observation techniques. By measuring a planet's mass through its gravitational effect on its star and its size through transits, astronomers can calculate its average density. High density suggests rock and metal. Low density suggests gas or water. Sometimes, atmospheric studies reveal hydrogen, helium, water vapor, or other gases, adding more pieces to the puzzle. Each measurement is a small clue, and together they form a portrait of a world no one has ever seen directly. When you really think about it, this is remarkable. From faint signals in starlight, scientists can figure out the size, mass, composition, and even weather patterns on planets hundreds of light years away. It represents a quiet triumph of human observation and reasoning, built on decades of careful work. These discoveries remind us that nature doesn't always produce neat categories. There's no sharp line separating rocky planets from gas giants or planets from brown dwarfs. Instead, there's a continuum A vast range of possibilities, shaped by formation histories and the complex dance of gravity, radiation, and chemistry. As our telescopes grow more powerful, we're exploring this continuum in greater detail, discovering planets that fill in all the gaps between the familiar types we thought we knew. Across the universe, planets don't just pick their favorite stars to orbit. Many worlds have chosen the strangest, most violent stellar companions you could imagine. When we first started hunting for planets beyond our solar system, we naturally looked around stars that seemed familiar, stars like our own sun. It made sense, really. We wanted to find something we could understand. But planets, it turns out, aren't picky at all. They'll form around almost anything, even stars that seem completely hostile to any kind of stable existence. The universe has a way of surprising us with just how adaptable these cosmic processes can be. Back in 1992, before we'd found thousands of exoplanets, before this whole field exploded into what it is today, astronomers made one of the most shocking discoveries in planetary science. They were studying something called a pulsar, which has the rather ungainly name PSRB 1257 plus 12. These objects are among the most extreme things in the universe, the leftover cores of massive stars that died in supernova explosions. Imagine taking more mass than our entire sun and crushing it down into a ball only about 20 kilometers across. The density becomes almost incomprehensible. As these objects spin, they shoot out beams of radiation from their magnetic poles, like cosmic lighthouses. When those beams sweep past Earth, we detect them as incredibly regular pulses, ticking away with the precision of an atomic clock. That precision is exactly what made the discovery possible. Astronomers noticed tiny variations in when those pulses arrived at Earth. The timing was shifting in subtle but regular patterns. After careful analysis, they realized something was tugging gently on the pulsar, causing it to wobble ever so slightly, that something was planets orbiting this stellar corpse. It was the first confirmed discovery of planets outside our solar system, and it wasn't around a nice, warm, yellow star like our sun. It was around the remnant of one of the most violent events in the universe, a stellar explosion that would have obliterated anything nearby. These worlds must be among the strangest places imaginable. A pulsar doesn't give off gentle sunlight like our sun does. Instead, it blasts out intense radiation and streams of high-energy particles. Any atmosphere on a nearby planet would be stripped away almost immediately. The surface would be constantly bombarded by radiation that would sterilize anything we might recognize as life. If you could somehow stand on one of these worlds, the sky wouldn't glow with steady daylight. Instead, it would flash on and off as the pulsar's beams swept overhead, like standing under a cosmic strobe light that pulses dozens of times per second. It's a scene that challenges our very notion of what a planet should be like. These worlds likely formed after the supernova explosion, from debris that settled into a disk and gradually came together into new planets. In a sense, they're second-generation worlds, born from the ashes of stellar death. There's something almost poetic about that. The way the universe takes destruction and transforms it into new creation. The fact that planets can form even after such catastrophic events tells us something profound about how persistent these processes really are. The universe seems determined to make planets, regardless of the circumstances. Pulsar planets are relatively rare though, at least among the systems we've been able to study. Much more common are planets orbiting red dwarf stars. These stars are smaller and cooler than our sun, and they actually make up most of the stars in our galaxy. If you could travel through the Milky Way, most of the stars you'd encounter would be red dwarfs, faint and incredibly long-lived. Red dwarfs burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. They're the marathon runners of the stellar world, while stars like our sun are more like sprinters, burning bright but dying relatively young. Because red dwarfs are so dim, the zone where temperatures allow liquid water to exist lies much closer to the star. Planets in this habitable zone often orbit at distances smaller than Mercury's orbit around our sun. This creates an interesting situation, one we've touched on before. Many of these planets become tidally locked, showing the same face to their star at all times. The TRAPPIST-1 system provides a fascinating example. It contains 7 Earth-sized planets, several of which lie in or near the habitable zone. These worlds orbit so close to their red dwarf star that their years last only a few Earth days. Imagine experiencing a full year in less time than it takes us to finish a work week. But proximity to a red dwarf brings complications. Many red dwarfs, especially young ones, are highly active. They produce powerful stellar flares that release sudden bursts of radiation. These flares can be far more energetic, relative to the star's size, than anything our Sun produces. A planet orbiting close to such a star would face frequent surges of ultraviolet and X-ray radiation. These could steadily erode away any atmosphere and would pose serious challenges for any potential life. It's like trying to maintain a garden while someone randomly blasts it with a flamethrower. Astronomers are still working to understand how planetary atmospheres respond to such harsh conditions. A strong magnetic field might help protect a planet, deflecting charged particles the same way Earth's magnetosphere shields us from the solar wind. A thick atmosphere could absorb some of the radiation, though it would undergo complex chemical changes in the process. Despite these challenges, red dwarf systems remain among the most promising places to search for habitable planets. They're incredibly numerous, and their small size makes it easier to detect Earth-sized worlds orbiting them. The dim light also makes it more favorable to study the atmospheres of planets that transit across their face. At the other extreme, there are planets orbiting stars much larger and hotter than our Sun. These massive stars burn brilliantly, but live fast, consuming their fuel in just a few 100 million years, rather than billions. A planet around such a star would receive intense radiation and might experience dramatic changes as the star evolves rapidly. These stellar giants eventually swell into supergiants before shedding their outer layers or exploding. The timescales for life to develop, at least as we understand it, might be severely limited in such systems. Yet planets can still exist there, shaped by the same fundamental processes that operate throughout the galaxy. Binary star systems add yet another layer of complexity to planetary existence. Many stars don't exist alone, but in pairs, orbiting around their common center of gravity. Planets in these systems might orbit one star, while the other shines as a brilliant companion in the sky. Or they might orbit both stars at once, following a path around the entire pair. These circumbinary planets, sometimes called Tatooine worlds after the famous fictional desert planet with 2 suns, have been discovered in several real systems. The changing positions of the 2 stars would create complex patterns of daylight and seasons. Variations in illumination could be quite dramatic, depending on how the orbits line up. The gravitational dynamics of binary systems can influence planetary orbits in subtle ways, sometimes making them more elliptical or causing gradual changes over time. Yet stable orbits are definitely possible, and the existence of these planets shows how adaptable planetary systems can be. White dwarf stars present another unusual stellar environment. These are the dense remnants left behind after stars like our Sun exhaust their fuel and shed their outer layers. What remains is a hot, compact core about the size of Earth, but containing a significant fraction of the original star's mass. For a time after formation, a white dwarf glows intensely from leftover heat, then gradually cools over billions of years. Planets can actually survive this transformation if they orbit far enough away from the dying star. There's evidence that some white dwarf systems contain planets or planetary debris. In several cases, astronomers have detected signatures of heavy elements in white dwarf atmospheres. This suggests that asteroids or small planets have been torn apart by the star's gravity and then consumed. There's even speculation that new planets could form from material shed during the star's final evolutionary stages, though this remains an active area of research. Neutron stars and magnetars represent even more extreme stellar environments. The intense gravity and radiation in these systems make them incredibly challenging places for planets to form or survive. Yet the discovery of pulsar planets reminds us that even the most violent cosmic events don't always prevent new worlds from emerging. When we think about planets around these exotic stars, it shifts our entire perspective on what alien worlds might be like. From the surface of such a planet, the star overhead might appear as a dim red ember, a brilliant blue-white beacon, a pair of dancing lights, or a rapidly flashing pulsar. The sky itself would reflect the nature of the host star, shaping the color of daylight, the pattern of seasons, and the energy available to power any processes on the planet's surface. It highlights just how adaptable planetary systems can be under wildly different conditions. Gravity, radiation, and chemistry operate according to the same laws everywhere in the universe. But the outcomes vary enormously, depending on the initial conditions and the stellar environment. A planet around a red dwarf might be tidally locked and bathed in dim infrared light. A world around a pulsar might endure intense radiation under a sky that strobes with regular flashes. A planet orbiting a binary star might see two distinct shadows stretching across its surface at the same time. Each of these environments pushes the boundaries of what we consider normal for a planetary system. Yet they're all natural consequences of the same physical processes we see operating everywhere. As astronomers continue discovering and studying these systems, they're not just cataloging new worlds, they're refining our understanding of how planets form and evolve under different conditions. The sheer diversity of planetary environments suggests that the processes leading to planet formation are remarkably robust. They can operate in settings far more varied and extreme than we once thought possible. This adaptability speaks to something fundamental about how the universe organizes matter and energy into complex structures. And amid all these extremes, there's a question that quietly follows every new discovery we make. If planets can exist in so many radically different environments, some harsh, some temperate, some wildly unstable, then what might this tell us about the limits of life itself? The universe seems almost determined to create worlds, regardless of the stellar circumstances. Perhaps life, too, is more adaptable and persistent than we've ever dared to imagine. Life on Earth exists in places that once seemed impossible. Deep beneath ocean surfaces, where sunlight never reaches, entire communities of organisms thrive around hydrothermal vents. These underwater chimneys spew water heated to over 300 degrees Celsius. The pressure down there would crush most things we know, yet microorganisms don't just survive, they actually flourish in these conditions. These tiny life forms have learned to use chemical energy instead of sunlight. It's a completely different way of powering life than what we see on the surface. Think about it. For billions of years, we assumed all life needed the sun, that these deep-sea creatures proved us wrong. Scientists have found life in acidic lakes that would dissolve metal. They've discovered organisms living inside Antarctic ice, where temperatures stay frozen year-round. Some creatures live in salt flats, where the water is so concentrated it should kill any living cell. Others exist kilometers beneath the surface, inside solid rock. These extreme organisms, called extremophiles, have adapted to heat, cold, crushing pressure, deadly radiation, and chemical conditions that would instantly kill most life forms. Each discovery forces us to expand our definition of where life can exist. This has completely changed how scientists think about other planets. Instead of looking for Earth's exact twin, researchers now consider a much broader range of possibilities. The question isn't whether humans could survive there comfortably. The real question is whether complex chemistry can happen in a stable environment over very long time periods. Water often gets called the most important ingredient for life. It works as an excellent solvent, letting molecules bump into each other and react. This is why scientists get excited about water worlds and planets in habitable zones around stars. But water alone isn't enough. Life also needs energy sources and chemical elements like carbon, nitrogen, oxygen, and phosphorus. On a water world with deep global oceans, energy might come from geothermal activity, just like those hydrothermal vents on Earth. If the ocean touches rocky material underneath, minerals could dissolve into the water, creating chemical gradients that tiny organisms might use as food. Even if layers of high-pressure ice separate the ocean from rock below, some computer models suggest that cracks or localized melting could still allow material to mix. There's something almost poetic about imagining life persisting in these hidden oceans, completely cut off from any star's light. Rogue planets drift through space between stars with no sun at all. These wandering worlds might still host underground oceans if they kept enough internal heat and had thick blankets of insulating ice. In such places, sunlight would play absolutely no role. Life would depend entirely on chemical energy and heat from the planet's core. These ideas remain educated guesses, of course. We haven't found direct evidence of life beyond Earth yet. The conditions required for life to begin in the first place are still mysterious. But discovering extremophiles on our own planet has shown that life can adapt to conditions far more varied than anyone once believed possible. When we look at hotter, more extreme planets, the possibilities become more uncertain. On lava worlds where temperatures reach thousands of degrees, it's hard to imagine any familiar form of life surviving on the surface. Essential molecules would simply break apart in that heat. Any complex chemistry would be rapidly disrupted. However, even in such harsh environments, there might be regions where conditions are less severe. On planets that always show the same face to their star, the boundary zone between permanent day and night might offer moderate temperatures. These narrow regions, sometimes called twilight belts, could theoretically support stable climates. This depends on many factors though, including how the atmosphere moves heat around and what the air pressure is like. It's fascinating to imagine these thin strips of potentially habitable land, caught between a blazing desert on one side and a frozen wasteland on the other. Planets, orbiting red dwarf stars, present another intriguing case. These small, dim stars produce dangerous flares and radiation. But some computer models suggest that thick atmospheres or strong magnetic fields could protect a planet's surface. Red dwarfs also live for trillions of years, much longer than our Sun. This means habitable conditions, if they exist, could persist for extraordinarily long periods. Time is one of evolution's most powerful tools. Given enough time, life tends to explore every available opportunity. The longer a planet stays habitable, the more chances life has to develop and diversify. There's also the possibility that life might exist in forms completely different from what we see on Earth. Most life here relies on carbon-based chemistry and liquid water. But scientists have speculated about alternative approaches to biochemistry. Some researchers have proposed that life could use solvents other than water, such as methane or ammonia, under the right conditions. Saturn's moon Titan has lakes of liquid methane on its surface. It's often mentioned as a place where such exotic chemistry might be possible, though no evidence of life has been found there yet. Whether similar possibilities could exist on planets around other stars remains an open question. The chemistry required for life is incredibly complex. While alternative forms are conceivable, they remain theoretical for now. Most searches for life focus on environments where liquid water and familiar carbon chemistry are likely to be present. One of the most promising methods for detecting life on distant planets involves studying their atmospheres from afar. Certain gases like oxygen, methane, and ozone can be produced by biological processes. If these gases are found together in specific proportions, they might indicate the presence of life. This works because these gases would normally react with each other and disappear over time. Finding them together suggests something is constantly producing them. Space telescopes can now analyze the atmospheres of some distant planets, searching for these chemical signatures. The process requires incredible precision and careful interpretation. Non-biological processes can also produce some of these gases under certain conditions. Nonetheless, atmospheric analysis, representing one of the most powerful tools we have for investigating life beyond Earth. When we ask whether life could exist on extreme worlds, we're really asking fundamental questions about adaptability and evolution. How flexible can life be? How many different paths might evolution take under different conditions? On Earth, life has diversified into an extraordinary range of forms. From microscopic bacteria that can survive in boiling water, to towering forests that reshape entire landscapes, to complex animals with intricate social behaviors. Given enough time and suitable conditions, evolution tends to explore every available possibility. If similar processes operate elsewhere in the universe, then life might adapt to environments completely different from Earth. It might exist beneath kilometers of ice, in deep oceans that never see starlight, or in atmospheres rich in gases we consider toxic. Life might rely on chemical reactions we haven't observed yet, or exist in forms that challenge our basic definitions of what living things are. The possibilities stretch our imagination in wonderful ways. At the same time, it's important to recognize that many extreme planets are probably completely sterile. Environments with intense radiation, wildly fluctuating temperatures, or rapidly changing conditions may not allow complex chemistry to persist long enough for life to emerge and evolve. The universe is vast beyond human comprehension. While life may be remarkably resilient, it's not necessarily inevitable everywhere. The delicate balance of conditions required for life to begin and persist might be rarer than we hope. Yet even if most extreme worlds turn out to be lifeless, studying them remains incredibly valuable. By understanding the full range of planetary environments, scientists can better identify the conditions that truly favor life. Each extreme planet acts as a natural experiment, showing what happens when temperature, pressure, gravity, and chemistry get pushed to their limits. There's something quietly inspiring about the idea that life, if it exists elsewhere, might be far more diverse than we can currently imagine. The universe is older and larger than any single planet or species. Its history contains countless opportunities for complexity and beauty to arise in forms we've never dreamed of. As astronomers continue studying planets around other stars, they're not just measuring sizes and orbital distances. They're searching for clues about atmospheres, climates, and the potential for habitability. Each new discovery brings us incrementally closer to answering one of humanity's oldest and most profound questions. Are we alone in this vast cosmos? Are we alone in this vast cosmos? For now, the answer remains beautifully uncertain, but the search itself has already transformed our understanding of the universe. We now know that planets are common throughout the galaxy. We know that environments vary far more widely than early astronomers imagined, and we're learning that the conditions suitable for life may be more flexible and forgiving than we once believed possible. When we first started finding planets around distant stars, nobody quite knew what to expect. The universe had kept this secret for so long, and suddenly we were uncovering worlds beyond our wildest imagination. What began as a simple search for confirmation turned into something much more profound. Yes, planets exist everywhere, scattered throughout the galaxy in numbers that stagger the mind. But these discoveries did something unexpected. They held up a mirror to our own world. Living on Earth day after day, it's natural to assume that what we see around us is, well, normal. The blue sky overhead, the changing seasons, the familiar rhythm of day and night. These feel like standard features, like the default settings of any planet. Yet when we peer out into space and examine these alien worlds, Earth suddenly doesn't look so ordinary anymore. Picture planets where the surface literally glows red hot from being too close to their star. Imagine worlds where one half bakes in eternal sunshine, while the other half remains frozen in perpetual darkness. Some planets drift through space completely alone, without any star at all, wandering through the cosmic void in total isolation. Against this backdrop of extremes, our planet starts to look less like the norm and more like a very special exception. The concept of the habitable zone, sometimes called the Goldilocks zone, becomes fascinating when you see how many planets miss it entirely. This is the sweet spot around a star where temperatures allow liquid water to exist. Too close, and the water boils away into space. Too far, and everything freezes solid. But here's where it gets interesting. This zone isn't a fixed boundary drawn in space. Atmospheres can completely change the game. Take Venus, sitting closer to the sun than we are, wrapped in a thick blanket of carbon dioxide. This creates such an intense greenhouse effect that the surface reaches temperatures of 460 degrees Celsius. That's hot enough to melt lead, and it's actually hotter than Mercury, even though Mercury sits much closer to the Sun. Meanwhile, Mars tells the opposite story, farther from the Sun with barely any atmosphere at all. Heat just escapes into space, leaving the planet cold and barren. When astronomers study these extreme exoplanets, they're essentially watching nature conduct experiments on a massive scale. Planets with atmospheres so thick they could crush a human instantly. Others with no atmosphere whatsoever, each one teaching us something new about how heat moves around, how clouds form, how chemistry works under different conditions. The size of a planet matters more than you might think. Get the mass wrong, and everything else falls apart. Too small, like Mars, and the atmosphere gradually leaks away into space. The planet simply doesn't have enough gravitational pull to hold onto its air. Too large, and you end up with something more like Neptune, a world buried under layers and layers of gas, nothing like the rocky surface we're used to. Earth sits right in that middle range, big enough to keep its atmosphere, but not so big that it becomes a gas. It retains heat from its interior, without staying geologically unstable for too long, and it's managed to support liquid water for billions of years. When we look at super-Earths and mini-Neptunes, we see how even small differences in size can lead to completely different worlds. Then there's the invisible shield, protecting us every day, Earth's magnetic field. Deep inside our planet, molten iron swirls around in the outer core, generating this magnetic bubble that deflects dangerous particles streaming from the Sun. Without this protection, those solar winds would gradually strip our atmosphere away, just like what seems to have happened to Mars over millions of years. This becomes especially important when we consider planets around red dwarf stars. These stars are smaller and cooler than our Sun, but they can be incredibly active, shooting out intense radiation. A strong magnetic field could mean the difference between a planet that keeps its atmosphere and one that loses it completely. The ground beneath our feet is constantly moving, reshaping itself through plate tectonics, volcanism, and the endless cycling of carbon between the air and the rocky interior. This geological activity acts like a planetary thermostat, helping regulate Earth's climate over enormous timescales. Without these processes, carbon dioxide might build up uncontrollably, creating a runaway greenhouse effect, or it might disappear entirely, plunging the world into a permanent ice age. On larger exoplanets, the intense gravity might actually prevent plate tectonics from working properly. The surface could become locked in place, unable to recycle materials between the interior and exterior. Thick atmospheres might create such crushing pressure that geological processes work completely differently than they do here. Earth's orbit around the Sun follows a relatively circular path, giving us stable seasons and predictable climate patterns over long periods. But many exoplanets follow highly stretched, elliptical orbits, swinging close to their stars and then racing far away again. Imagine living on a world where temperatures swing from scorching hot to freezing cold as the planet moves through its year. The climate would be chaotic, unpredictable, probably hostile to complex life. Our moon plays a role that's easy to overlook. It acts like a cosmic stabilizer, keeping Earth's axial tilt relatively steady. Without this large companion, our planet might wobble chaotically, causing dramatic climate shifts that could make complex life nearly impossible. Not every planet has a large moon, and this absence could create environments vastly different from what we know. All these factors work together like instruments in an orchestra. Distance from the star, atmospheric composition, planetary mass, magnetic field strength, geological activity, orbital stability, even the presence of moons, they all have to harmonize to create conditions suitable for life. As we know it, extreme exoplanets show us what happens when one or more of these elements goes out of tune. These aren't just cosmic curiosities to marvel at from a distance. They're natural experiments happening on a scale we could never recreate in any laboratory. Each one tests different combinations of physics, chemistry, and astronomy, showing us the full range of what's possible when you mix matter, energy, and time across billions of years. There's something profound about this perspective shift. For most of human history, we assumed Earth was the center of everything, uniquely crafted for life in an otherwise empty cosmos. Discovering other planets, first in our own solar system and then around distant stars, gradually changed that view. Now, with thousands of known exoplanets, we see that Earth is one member of an enormous, diverse family. But this realization doesn't make our world less special. It makes it more precious. By comparing Earth to these extreme environments, we can see more clearly just how remarkable our particular combination of conditions really is. Liquid oceans that have persisted for billions of years, a climate gently moderated by atmosphere and geology, a protective magnetic field, a stable orbit around a relatively calm star. None of these features are guaranteed. They're the result of countless variables aligning over vast stretches of time. This doesn't necessarily mean Earth is unique in the universe. There could be many worlds with similar conditions scattered among the stars. But it does remind us that such conditions aren't inevitable. They're not the default setting for planets. Studying extreme exoplanets also gives us glimpses into Earth's own future. Some of the processes we observe on distant worlds might eventually happen here, though on timescales far longer than human civilization has existed. Our sun will gradually grow brighter over the next few billion years, slowly increasing Earth's temperature until eventually the oceans boil away completely. Venus might represent a possible future version of our planet, though thankfully that's an almost unimaginably distant prospect. Understanding how atmospheres evolve, how greenhouse effects spiral out of control, how planets lose their water to space, all of this provides insights into the long-term changes awaiting our own world. In studying these distant planets, we're also studying the deep future of Earth itself. There's an emotional dimension to all this as well. Astronauts who have seen Earth from space often describe a profound shift in perspective. Our planet appears small, blue, and fragile against the vast darkness, its thin atmosphere like a delicate soap bubble protecting everything we've ever known. Extreme exoplanets reinforce this sense of precious fragility by showing us just how harsh most cosmic environments really are. At the same time, these discoveries expand our sense of what's possible. The universe isn't limited to one type of world or one set of conditions. It contains planets of fire and ice, worlds of endless storms and perpetual calm, places shrouded in darkness and others bathed in multiple suns, each one shaped by the same fundamental laws of physics, yet expressing those laws in wonderfully different ways. This diversity invites wonder rather than worry. It encourages us to keep exploring, to keep asking questions about how planets form and change, and how life might find ways to emerge under conditions we've never imagined. The universe, it turns out, is far stranger and more varied than we ever expected, and our small blue world sits right in the middle of this cosmic symphony, playing its own unique and beautiful note. The universe operates on a scale that stretches the boundaries of what our minds can comfortably hold. When we think about the sheer number of worlds spinning through space, each one following its own unique path, it becomes clear that our corner of existence represents just one note in an impossibly vast symphony. Every star we see carries with it the potential for planets, and many of those planets harbor conditions so extreme they challenge everything we thought we knew about how worlds can exist. Consider the planets where oceans of molten lava stretch from horizon to horizon, their surfaces glowing with heat so intense it would vaporize most materials we encounter in daily life. These aren't worlds of destruction, though they might seem that way at first glance. They're simply operating under different rules, shaped by forces that dwarf anything we experience on Earth. The lava flows in patterns determined by the same physics that govern water flowing down a hillside, just at temperatures that transform rock into liquid. Then there are worlds locked in eternal twilight, where one side faces their star in perpetual day, while the other remains frozen in endless night. Between these extremes lies a narrow band where temperatures allow for conditions we might recognize, though even there the landscape would feel alien. Winds howl across these boundary zones at speeds that make our strongest hurricanes seem like gentle breezes, carrying heat from the blazing day side to the frozen night side in a never-ending cycle. The detection of these distant worlds relies on light that has traveled across distances so vast that the numbers become almost meaningless. When we observe a planet orbiting a star hundreds of light years away, we're seeing it as it existed when that light began its journey. The planet we're studying might have changed dramatically in the time it took that information to reach us. Its atmosphere could have shifted, its surface could have been reshaped by geological forces. Yet we remain connected to it through these ancient photons carrying their message across the void. Some planets drift through space without any star to orbit, rogue worlds cast out from their original systems to wander alone through the galaxy. These orphaned planets experience a kind of cosmic solitude that's difficult to imagine. Their surfaces, if they have solid surfaces at all, exist in temperatures approaching absolute zero, lit only by the faint glow of distant stars. Yet even in this apparent desolation, these worlds follow the same physical laws that govern everything else, their atoms still vibrating, their gravity still present, their existence still part of the grand pattern of the universe. The storms that rage on some distant worlds dwarf anything in our experience. Jupiter's great red spot, a hurricane that could swallow Earth several times over, seems almost quaint compared to the atmospheric chaos found on certain exoplanets. These storms can persist for centuries, driven by temperature differences and atmospheric dynamics that operate on scales we can barely comprehend. The winds don't howl, of course, since sound cannot travel through the vacuum of space. But their effects reshape entire hemispheres over geological time. Our ability to detect these worlds has grown remarkably in just a few decades. The techniques we use depend on incredibly subtle measurements, detecting the faint dimming of starlight as a planet passes in front of its star, or the tiny wobble a planet's gravity induces in its star's position. These signals are so weak they require instruments of extraordinary precision, yet from these whispers of data we can deduce the size, mass, orbital period, and sometimes even atmospheric composition of worlds we will likely never visit. The chemistry that governs these distant worlds operates according to the same principles we observe in laboratories on Earth. Carbon behaves the same way whether it's forming diamond in Earth's mantle or creating complex molecules in the atmosphere of a planet orbiting a red dwarf star. Water follows the same rules whether it's flowing in terrestrial rivers or potentially existing as subsurface oceans on moons around gas giants thousands of light years away. This universality of physical laws creates a kind of cosmic familiarity, even in the most exotic environments. Time moves differently across the universe, not because of relativity, though that plays a role, but because of the sheer scales involved. Processes that seem rapid to us unfold over millions or billions of years on cosmic scales. Mountain ranges rise and fall, atmospheres evolve, entire planetary systems mature and age, while light from distant stars continues its patient journey through space. This unhurried pace of cosmic change offers a different perspective on the urgency we often feel in daily life. The darkness between stars isn't empty in the way we usually think of emptiness. It's filled with particles, magnetic fields, and the occasional wandering asteroid or comet. But more than that, it's filled with potential. Every cubic meter of seemingly empty space contains the basic ingredients for complexity, waiting for the right conditions to assemble into something more organized. Stars form from this apparent nothingness, gathering material until nuclear fusion ignites and illuminates the surrounding region. When we consider our place among all these worlds, Earth emerges not as the center of everything, but as one remarkable example among countless others. Our planet's conditions allow for liquid water, stable temperatures, and a complex chemistry that supports life as we know it. Yet the universe has created worlds with conditions far more extreme, suggesting that our definition of habitability might be far too narrow. Life, if it exists elsewhere, might thrive in environments we would consider utterly hostile. The same atoms that form our bodies were forged in stellar cores billions of years ago, scattered into space when those stars died, and eventually incorporated into the swirling disk of material that became our solar system. Every element heavier than hydrogen and helium in our bodies has this stellar heritage, connecting us directly to the cosmic processes that shape planets around distant stars. We are, quite literally, made of star stuff that has arranged itself into forms capable of contemplating the universe. The light from stars continues to travel toward us, carrying information about worlds that may have changed dramatically since those photons began their journey. Some of the stars we observe may no longer exist, having exhausted their fuel and collapsed, or exploded long ago. Yet their light persists, maintaining a connection across time and space that allows us to study cosmic history. We see the universe not as it is, but as it was, creating a kind of temporal archaeology written in starlight. As our instruments become more sophisticated, we discover planets that challenge our assumptions about how worlds can form and evolve. Some orbit so close to their stars that their surfaces are molten, while others exist in such distant orbits that they receive less warmth than the coldest regions of our outer solar system. Some have atmospheres composed of vaporized metals, while others may have skies filled with clouds of precious gems. Each discovery expands our understanding of what's possible in the universe. The journey light takes from distant stars to our telescopes represents one of the most patient forms of communication imaginable. These photons travel for years, decades, or centuries, maintaining their integrity across vast distances until they encounter the mirrors and sensors of our observatories. In that moment of detection, we complete a connection that began when the light left its source, creating a bridge across space and time that allows us to study worlds we will likely never visit in person.